we are talking about a dynamic system that mimics a bow acting on a string of a violin. So the system is the following. You have a box and tied to a spring on the left, and the box is put on a conveyor belt. So the belt is moving to the right at a constant speed, and here we only draw part of the belt. And you can imagine the belt is really long, and the box never falls off. So the whole system is that we care about is actually in one dimension. So here I want to talk a little bit about the Newton's law. The Newton's equation F equals ma is really a vector equation, and the force is, you have a direction and you have a magnitude, and the magnitude is a positive number. The force is always a positive number. But when we study a one-dimensional system, we usually write just a scalar equation. What this scalar equation really means should really be a vector equation. So, but because the constant vector to the right doesn't really do anything, so we just don't write it out anymore. But the thing is, if we kind of assume the direction is always to the right, then we allow the force, the magnitude of the force, to be negative. So if a negative value of force F, it just means a force to the left. With this said, I can start talking about the parts of the systems. First thing, we have a spring, and assume that when the spring is relaxed, the position of the box is at 0, and if the position of the box is at coordinate x, then the spring is pulling the box to the left and with a magnitude of k times x. For the belt, it works like the following. So first thing, you imagine that the belt is not moving, it's a still. If the box is moving relative to the belt to the right with velocity v, the box will receive a friction force. It's called a sticky friction force to the left, and the magnitude is f of v. And here is the graph of f. So when v is 0, that is, the box is not moving relative to the belt, the force is 0. And when v is positive, so when v is to the right, the force is positive to the left. And this is part of a parabola. Let's try to write down the differential equations of the system. Some known constants are the constant of spring and the mass of the box, and the belt is moving to the right at a constant speed b, and the sticky friction is characteristic by the function f, which is known. So the variable here is x, and it describes how far away the spring is stretched to the right, away from its relaxed position. So the spring force is to the left, which is kx. The sticky friction force, from the belt, is also to the left, because we are imagining that the box is moving to the right relative to the belt. So the speed of that relative to the belt is given by the speed of the box minus the speed of the belt. Now Newton's equation is written as the force equals ma, the acceleration. And the reason we have this negative sign is because the Newton's equation kind of assumes the force is to the right, but our force is to the left, so they differ by a negative sign. Next, I will graph the solution using Euler method. But Euler method can only be applied to differential equations of first order. So that is, you only differentiated the variable once, but we have the second derivative, and that can be resolved by denoting v as x dot and substitute v equals x dot into the original differential equation to get the second differential equation. Now we have a differential equation about x position and v velocity. Now we only have the first derivative. I will use the Euler method to graph x and v with respect to t. I will also graph the velocity and a position xv in its phase space. So in this coordinate, there's no timeline. So the way that we graph it, we start from an initial value of position and velocity, and based on the differential equation, we go to the next point, and then we go to next point. Okay, let's see the graph of the system. This is the graph that characterize the sticky friction of the belt. It is the graph of F in the equation. And with that sticky friction and these initial values, this is the graph of the system. So the horizontal axis is time t, the vertical axis is position for the blue line, velocity for the red line. We notice two things. First, it is periodical, so it is oscillating. This is hardly surprising. So what is surprising is you might ask, what is this part? You have this thick part. So the thick part is actually the red line is moving zigzagging here very fast. So that's why you see a very thick line. So the red line is going up, down, zigzagging. So it is zigzagging around the value 2. What is 2 here? So 2 is our belt speed. So this is the part that the speed of the box is equal to the speed of the belt. So the box is going along the belt. Apparently the speed is zigzagging around 2. So you can see that the blue line, which is the position, it is moving smoothly to the right. But the speed is kind of struggle a little bit. It is trying to stay at 2. The speed is varying around 2, but the box is still moving smoothly to the right. Now let's see this process in the phase space. So the horizontal axis is position, the vertical axis is speed. Let's trace out. We start at the position, so 1, speed 0. And if we increase time, this is the trace I want to show you. So what we see here is the state of the system end up in a cycle. So this cycle is the limit cycle of the system. So when you see a cycle like this, it kind of corresponds to a periodic graph like this. Now let me change the initial value of the state and trace it one more time. Let's do this with another value. The point of this video is really just give you another example of a nonlinear system and show you this limit cycle thing. So this limit cycle, they would appear again and again in your study of nonlinear systems. Now, on a side note, that I copied this example from a book, and in this book, the book does not mention at all about this thickness thing here. So it is surprising to me to see that the speed of the box is zigzagging around the speed of belt when the box is going along the belt.